Partition equals subset sum. This problem looks innocent. And then Rex timelines. Partition equals subset sum is a pattern mastery 100 star, because it tests whether you can recognize a hidden subset sum dynamic programming problem and reason about time-space trade-offs on the fly. Good news! With a basic framework and a slick 1D DP, you'll narrate and code this confidently, no brute force backtracking meltdown. Breakdown. We get an array of positive integers called nums. Can we split it into two subsets with equal total? If the total sum is odd, the answer is immediately false. Otherwise, we just need to know whether some subset sums to total divided by 2, classic subset sum. Assess. Backtracking is exponential. Instead, we use dynamic programming. Define dp of s as can we make sum s using the numbers we've seen so far? Initialize dp of 0 as true. For each number x, update dp of s by checking dp of s minus x, going backward from target down to x, so we don't reuse x multiple times. The complexity is O of n times target in time, and O of target in space, where target equals total divided by 2. A neat alternative is a bit set that shifts reachable sums with bits OR equals bits shifted left by x. Structure. Compute the total. If it's odd, return false. Set target to total divided by 2, and create dp of length target plus 1 with dp of 0 set to true. For each x in nums, iterate s from target down to x, and set dp of s to dp of s or dp of s minus x. Return dp of target. Let's try to implement it using solution 1. We're defining a function called can_partition that takes an array nums. We start by calculating the total sum of all numbers in the array. If the total is odd, we immediately return false, because an odd number can't be split evenly into two equal sums. If the total is even, our goal becomes finding a subset that sums to half of the total. So we set target to total divided by 2. Now we create a Boolean array dp of size target plus 1, filled with false. dps will mean, is it possible to form sum s using some of the numbers so far? We set dp0 to true, because we can always form sum 0 by choosing nothing. Now we loop through each number in nums. For each num, we loop s backward from target down to num. We go backward so we don't reuse the same number multiple times in one pass. Inside the loop, if dps num is true, that means we can already form s num, and by adding num, we can form s. So we set dps to true. After processing all numbers, we return dp target. If it's true, we can form half the total, which means the array can be partitioned into two equal subsets. Time complexity is O(n) target, because for each number we may scan up to target. Space complexity is O target because we only store the dp array. Let's verify solution 1 for partition equals subset sum. Input is nums equals 1, 5, 11, 5. The total sum is 1 plus 5 plus 11 plus 5, which is 22. 22 is even, so the target is 11. We set dp0 to true, and everything else starts as false. Now we process each number. With num equals 1, we can make sum 1, so dp1 becomes true. With num equals 5, we can make sum 5, and also sum 6 by using 1 plus 5. With num equals 11, we can directly make sum 11, so dp11 becomes true. Since dp11 is true, that means we can form the target sum 11. So we return true. The output is true, and the expected is true. They match, so solution 1 is correct for this test case. Let's try to implement it using solution 2. We're defining a function called can_partition that takes an array nums. We start by calculating the total sum of all numbers. If the total is odd, we immediately return false, because an odd total can't be split into two equal integers. If the total is even, we set target to total divided by 2, because we just need to find one subset that sums to target. We create a map called memo to store results of subproblems, so we don't recompute the same state again. Now we define a recursive function dfsi. Cur. I is the current index we are deciding on. Cur is the current sum we have built so far. If cur equals target, we return true because we found a valid subset. If cur is greater than target, or I goes past the end of the array, we return false. We build a unique key using I and cur, like I, cur. If this key is already in memo, we return the stored answer. Otherwise, we try two choices. Take the current number, which calls dfsi plus 1, cur plus nums I, or skip the current number, which calls dfsi plus 1, cur. If either choice returns true, then we can reach the target from this state. We store the result in memo and return it. Finally, we start with dfs 0, 0, and return its result. Time complexity is about O(n) target, in practice because memoization limits repeated work. Space complexity is O(n) target, because we store memo states and use recursion stack. Let's verify solution 2 for partition equal subset sum. Input is nums equals 1, 2, 3, 5. The total sum is 1 plus 2 plus 3 plus 5, which is 11. 11 is odd, so we immediately return false without running DFS. The output is false, and the expected is false. They match, so solution 2 is correct for this test case. Let's recap partition equal subset sum. This is one of those problems that looks like split the array, but the real challenge is spotting the hidden subset sum structure. We're asked whether an array can be divided into two subsets with the same total sum. The key observation is that this becomes a single goal. If the total sum is odd, it's impossible right away. If it's even, we only need to know whether there exists a subset that adds up to half of the total. We compared approaches and saw why brute force backtracking doesn't scale. It grows exponentially. Dynamic programming gives a controlled, efficient solution by tracking which sums are reachable as we process the numbers. That shifts the problem into a predictable O of n times target approach, and we also noted a bit set trick that performs the same reachable sum idea using bit shifts. The structure is clear. First reject odd totals, then set the target to half the sum. Next, build a DP table of reachable sums starting from a base case where 0 is always reachable. For each number, update the DP values backward so each number is only used once, keeping the logic consistent and preventing accidental reuse. We implemented the one-dimensional DP approach successfully on LeetCode without errors, by expanding reachable sums step by step as each number was processed. Starting from DP0, as true, we marked new achievable sums efficiently while keeping memory use low. LeetCode test cases confirmed correctness. Inputs that conform an equal partition returned true, and impossible cases returned false. For example, 1, 5, 11, 5, correctly returned true, while 1, 2, 3, 5 returned false immediately due to an odd total sum, matching expected behavior. The takeaway is that many divide the array problems are really subset sum problems in disguise. If you learn to recognize that early, you can replace a messy recursive search with a clean, disciplined dynamic programming solution that's efficient and interview ready.